Good day to you all. We are going to talk about certain practical issues in designing distillation processes. So far what we have covered are the basics of engineering design and process design. This we have followed with a special type of separation process design, which is designing of distillation separation, where we have specifically covered initially, to start with, we talked about flash distillation or flashing. This has been followed with fractionator and fractionator design, and in the last class you have been given input on the basics of batch distillation and its design and operation to some extent. Today what we are going to decide is about the practical issues normally that is faced by the designer while he is engaged in designing of such distillation separation processes. To start with, what we say is very often he is supposed to handle multi-component separations. Say they have a mixture of A, B and C. This is in the order of decreasing volatility, and perhaps he is supposed to produce 3 streams, rich in A, rich in B and rich in C. So the question comes that what should be the sequence of separation and what are the options? That we definitely have to cover in this course, because this is a very common situation which is faced by the designer. The next option that comes is almost equally important, that's selecting the process. When to select flash, when to select fractionation, when to select the batch distillation. The inputs on these, they have already been given to you while these topics were discussed, but I will try to consolidate here and include a few heuristics on that. We definitely have to talk about optimum design. That means just delivering the functionality is the basic requirement, but it has to be delivered efficiently, particularly with an economic consideration, which is the essence of any engineering design and differentiates the engineering design from a science-based design. We certainly have to take care of the functional aspects of the design output. The plant that one designs, the distillation setup that one designs has to be erected, it has to be commissioned safely, economically, with the available resources. It has to be produced efficiently, that means it has to be operated in the production phase, and which obviously means there will be startups and shutdowns. So all these facilities have to be there in the process that you design. So your distillation process should consist of considerations for erection, commissioning, production phase, startup and shutdown. In fact, typically the startup and shutdown require certain additional facilities which possibly will not be used during the operational phase. And at the end, you definitely will be arriving at a finalized designed output, and that you have to judge that how good your final output is, whether your design is stable or not. That also we will be covering today and having an idea about it. To start with, we start on today's first topic, which is sequencing multi-component separation by distillation. The first configuration that you see here is basically what? It uses a single column with a side stream draw, with a side stream draw. That means the components rich in A is the top product, the component rich in C is the bottom product, and possibly there will be some composition on a tray which will meet the requirement of the stream as a product with an adequate concentration in B. Let us look at the advantage of using a single column. Obviously, your involvement of finance is less. That means you require only minimal amount of investment because you are going to use a single column. But your operation is slightly more complicated, particularly controlling the quality of A, B and C together. It requires a little bit of in-depth knowledge of the distillation process itself. But in any case, we already have dealt with simple columns which produces only a top and a bottom product, and more or less the similar process can be used in case of this particular side stream draw columns. One thing you must remember, that this quality of B depends on how much you draw as a side stream. From the side stream draw tray, if this be your side stream draw tray, which I am drawing here like this, and the side stream will be drawn here, and whatever you do not draw will be falling here as an internal reflux. And this is your stream B. You will notice one thing, whatever liquid falls on this, if the entire amount is drawn out as B, the internal reflux would dry out. That means it will make these trays ineffective. That means there is a limit up to which, if you have to maintain a quality of B, you can draw, and that is slightly more complicated as compared to operating your straight column. Often there are other options of separating A, B, C mixture into streams rich in A, B and C. The next one is here, which is called direct sequencing. This definitely, and it is very obvious that it is using two columns, the first column and the second column. The first column top product is the lightest, which is A. The bottom from the first column goes to the second column, which is again split into two streams, which is again a fractionator, and it is B which is produced at the top of the second column, and whatever remaining is your product C. That means here there is one big advantage, perhaps you should ask me, that why use one additional column. The first advantage that you have is you can check and change the split between this stream and this stream more easily, because this stream particularly becomes independent. If you want to have a larger variation in the quality of B, it is possible in this direct sequencing operation. There are quite a few other advantages also. That is, if you look at the throughput of the column 1, the feed is the entire quantity F, whereas the second column has got a much smaller feed. That means you expect the second column to have a lower diameter or a thinner column, which is expected to be cheaper. In some cases where you want a greater flexibility between the split of B and C products, you have a large amount of A present there, that makes the second column substantially smaller in diameter. In such cases, direct sequencing is definitely of help. So, we know now that the first option that comes the cheapest possibly is the side stream draw, the other option is the direct sequencing. Similar to direct sequencing, it is also possible to have an indirect sequencing, which is this particular option. In indirect sequencing, what we take first is the bottom from the first column, which is the stream C. The top product is a mixture of A and B, which is split in the second column. The same logic applies here too. What you have is, if you are taking out if your feed contains a good amount of C, so if you take that large amount of C to get out from your mixture, you are left out with a very small quantity of F, which is a mixture of A and B primarily, which can be split into two streams in a well controlled fashion in your fractionator 2. So, one advantage of this is, or rather by looking at the direct sequencing and indirect sequencing, we can see that such a sequencing method becomes very useful in reducing the investment cost when one of the product is in large quantity. So, if you take it out the large quantity first, the later columns that you have to add are usually of a smaller diameter, and that helps the economics. But in any case, this could be an advantage only when the separation is rather important between either B and C in case of direct sequencing and A and B in the indirect sequencing case. So, I would like to say that though I have given you an example of fractionation where the sequencing is implemented, but similar thing is true in case of batch distillation also. In case of batch, you can produce in a set of accumulators products which are rich in A, B and C, or you can run a batch, take out the product from the top and the bottom and rerun either top or the bottom, similar to the direct sequencing or indirect sequencing. Naturally, these are the options. In case of batch distillation, with stages, normally the side stream draw is not very economic, because as such batch separation or batch distillation is used when the extent of separation required is not very high. What we do now is we move forward to the next thing, and here what we do is we look at a set of heuristic rules and certain information. This heuristics will firstly try to relate what to choose from batch, fractionation or flash. You already have been given an input while being taught the batch distillation process that it is usually economic in small capacity. It is usually economic in small capacity. This requires startups and shutdowns, because you have to fill your batch steel, run it, shut it down and make it ready for the next batch. So, quite naturally, if you lose by off spec, you lose one batch material only as off spec. So, your better control is always there in case of batch distillation systems. But at the same time, you can have flexibility of changing the product and the feed quality depending on what is demanded and what quality of feed is available to you for the same set of equipment. Quite often, batch distillation in presence of such uncertainties in the feed and the product quality specifications is quite important and efficient. You will also look at another case where the batch distillation is important. Very often you will find there are streams which are contaminated with either a high boiling or a volatile product. Say a heavy oil is mixed with gasoline. The boiling point difference is substantial. The quantity of gasoline is small. So, in such cases, possibly what you will do is you will simply use a batch distillation, which you will be using either a single stage batch still or maybe one with multiple stages, but it will be effective in separating when the volatilities are substantially different, and they are quite effective when you have separate the contaminants or the impurities. You will notice one thing: the moment we say impurity, the quantity of impurity is small. So, usually you will find batch distillation being used for systems where one product dominates compared to the other. Like either your distillate is small or what you're leaving at the end is also substantially small. But remember, while distilling something in batch, you have to ensure that your heating element has to remain submerged when the last drop comes out. That means you cannot have 99% of the distillate in a batch operation. Possibly you can go up to some 15-20%. That's a practical limit, mainly posed by requiring the heating elements to remain submerged in the batch still. We also know that similar to the batch, the simplest form of distillation is a flash distillation. It is certainly the cheapest alternative, but we have a limitation here. That means the vapor and the liquid, they get separated using only a single stage. So, if your single stage enrichment is sufficient for the feed, then only you can use the flash distillation. But one big advantage is it's a cheap alternative, easy to operate. What you have to control basically is the flash drum pressure, and we'll see a little more details about this in the next few slides. The quality which is produced with respect to the purity of the vapor, it may not be a very precisely controlled even. We have a very important question in our hand. The economic option. Quite naturally, the designer has to choose between options of flash, fractionation and batch. And he has got a separation problem by distillation at hand. It is obvious that you have been taught that there are ways to optimize the fractionation, there are ways to optimize the batch, and there are ways to optimize the flash also, which we have not dealt in detail. But anyway, it is true, and you have to appreciate at this particular point, and we do know that if I decide on a fractionator to be designed for a particular separation, there will be an economic optimum design of the fractionator. So, when you look at the best option, you should look at the best economic option of flash, the best economic option of fractionation, and the best economic option of the batch, and then only compare. So, basically the optimum or the final global economic optimum needs to be chosen among the best optimized options, of flash, fractionation and batch. Here is a big boon to us. While we are talking about multi-component fractionation, we have outlined a shortcut design procedure, which is basically the Fensky-Underwood-Gilliland method. It is the Fensky-Underwood-Gilliland method, and it is not only that you can have a separation of a multi-component distillation calculated by this method, it can also be applied roughly to binary systems also. So, this particular method of design is quite sufficient to evaluate or compare the economic optimums. So, with this we move forward in the list of heuristic rules and other things. The designer, often you will always find that he will not opt for the most economic option. He has other considerations which may even override the economic optimum. The best economic option is not opted in certain cases. Such cases are based on subjective considerations, which may include ease of operation, proven technology and reliable design. Similar plants existing in the same complex, so you do not have to train your manpower again on a new plant. The ease of maintenance, which you normally find whenever you are choosing a particular technology, you contact its users, find out how easy it is to maintain and run the plant, how good it performs in practice, and definitely if you have similar plants in the same complex, you will have the advantage of common spare. For example, you did not have exactly the same capacity column which you find to be optimum. You may go slightly away from the optimum design and have another column which is identical to one which is remaining in your plant already, so that you can use common spares of heat exchangers, maybe columns and other spare parts. The thumb rule also tells us, which is again too obvious, the separation by distillation at a lower pressure is easier. Yes, it's true. It's always true that since the XY diagram, here if I have X and if we have Y, and this is my 45-degree line, at lower pressure it is this, and as pressure increases it goes further away. So this is the increasing pressure. So what you have here is basically, sorry, I made a mistake. It's basically decreasing pressure. Sorry, the pressure decreases this way. So what happens is like this. No, I'm repeating this particular slide once more. We continue with the heuristic rules. Practical considerations often override the computed economic optima. That means, even if I have decided on a particular design of a plant, we do not go for it. We may use certain other subjective considerations which could be ease of operation, which could be ease of operation, a proven or a reliable design to be adapted, similar plant in the same complex, ease of maintenance or the common spare, etc. Separation by distillation at lower pressure is always easier. What happens is, at a lower pressure, the XY diagram deviates more from the diagonal line. So if I have X here, if I have Y here, in this direction, this one will have a lower pressure as compared to this. That means the pressure increase is this way. That means this gives us one suggestion. We should always try to design a plant which will operate at the lowest operating pressure, but there are certain limitations with respect to this which the designer considers. In a real life distillation column, there will always be some leakages through the flanges, fittings, valve glands, etc. So if it is a operating pressure which is above the atmosphere, the content inside, the vapor inside will be leaking out, and if it is operating under vacuum, air will be leaking in. So the next point that we have to say is, you will have the non-condensable gases that are present in the system due to either air inleak, air dissolution in the feed tank, cracking, or other reactions. Vacuum columns are preferred for high boiling point and heat sensitive compounds, because it reduces the boiling point and the operating temperature of your column, and naturally the bottom temperature in a vacuum column being the highest, we definitely will be having a limiting maximum temperature for the column bottom temperature in case of vacuum columns, and for other columns also, particularly when the bottom product is a heat sensitive material. Then the basic considerations during the design for the designer are safety, economy, and the resource availability. The functionality that the design has to cater are during erection, commissioning, and the operation, which includes the production phase, startup, and shutdown. There is one more thing which is very important, the flexibility in the operation of the design that is finally realized. It has to cater to variation in feed quality, the product quality demand, and certain uncertainties in the design inputs. So, we definitely have to be concerned about designing a plant in presence of uncertainties in the inputs to the design. I just would like to add two things here. I will talk about the startup and shutdown. In case of a fractionator, we normally have the column here. We have a condenser from where the liquid which condenses in the condenser comes to the overhead drum. From there, part of it is taken out as distillate and a part of it is sent in as reflux. It could be R or L, whatever it is. I will also have here a reboiler. From here the vapor will be returned and we will be taking out a bottoms from here, and here is my feed. Now, we have to have heating of my feed. That means the entire heating normally is not by the reboiler. The one reason which is there is basically the highest temperature in this system is here. The feed is at an intermediate temperature. So, what you normally will be having is a heat recovery scheme which will go like this. It will recover heat from the bottoms and send the bottom out like this. You have possibly other heating arrangements and exchangers in your feed line also. You definitely will be having a feed pump here, which will be pumping the material which will be coming from some external source, possibly from a tank. Now, when you start your pump, when you start your unit, everything is cold. In order to have the temperature in your column, what is done? You usually will have a line drawn from here, which will be drawn from here and connected to the suction of the feed pump. This is the start up line. This is fitted with a valve. In fact, it is fitted with a globe valve and it is also fitted with a gate valve. So, what happens is when you start your feed, nothing vaporizes. So, it comes here. The entire thing is again drawn from the bottom and is sent here. So, what you actually will be having here is one more pump which will be like this. So, this pump will be started once you have sufficient level here. It sends the entire thing back to the feed line, which keeps on circulating. So, what happens is with time, since it circulates through the reboiler, which has to be kept on by that time, its temperature goes up, the vapor starts forming, it goes up the cold column, condenses in the walls and the trays of the cold column and starts coming back. There will be after some time when the entire column will get heated and liquid will start coming into your reflux drum and your reflux drum will be having a level. Quite naturally, since some of the liquid which had come here while it is circulating, part of it gets transferred to the reflux drum, you have to take fresh amount of feed. During this period, this startup line circulation goes on, and gradually what you find as you have the temperature in your top which corresponds to your distillate composition, what you do in that particular case is you gradually shut this particular flow and open the flow going to the storage of B. So, this is how you start up fractionators. This is a very brief idea just to give you the fact that not only there are facilities for operating under normal condition, but for your startup you may require in your plant additional facilities like the startup line in your fractionator. I leave it to you to think that how will you gradually shut your plant down. Possibly now it is time for us to talk about certain uncertainties in the design input. The flash design system will have its input as design inputs as flash feed rate, XF is the feed composition, the feed condition TFPF, and the flash drum pressure is also stated in this particular case, and my functional requirement is my after flashing my drum overhead vapor should have a composition of YD, and this is my XP and this is my F. Now, if you look at the design procedure, the value of F, the value of XF, the value of TFPF and the P flash, they all are unique values. These are the best estimated unique values based on which you have given your design. That means your XP, your YD that you have found out and the design dimension of your equipment that you have found out depends on certain set of unique values of input that has been decided. But it is true that there will be certain uncertainties associated with each of these. That means, if I have a variable here, it could be feed, it could be 10 meter cube per hour, possibly this value, this is 10, but it could be 9.2 to maybe 10.8. And probably the maximum probable value has been 10. This is 9.2 and this one is 10.8. So, what I would like to say here is, even though we use unique values for my design, I have to test my output YD after the design has been done, that what is the effect of YD, what is the effect of these input variations on YD. That means, we are supposed to report variations in YD with respect to the change in F, the change in YD with respect to changes in XF, and naturally so on. As long as the changes are small, it is easy and it is linear, and you can very easily either do a simulation or repeat a hand calculation and you find out. And but if you are finding that all these changes are not much are not much affecting your YD, what you expect to get is a YD which will have a distribution something like this. This basically is your YD. This basically is the frequency, or rather the probability of variation of YD, and quite naturally, if you have a probability distribution of YD because of the variations of these inputs like this, or if you have another where it is much steeper, this simply shows that this simply shows that this is a much more stable design. That means the design output is not affected by the input changes. I think with this I will be stopping, and before that I only say that the mean and the standard deviation for YD is the parameter which is normally checked for this. Thank you.